warning will be given at 8 minutes, and followed by that there will be a 2-minute interaction with the speaker. So there will be 3 contributory lectures, as I told, CL100, CL101 and CL102. So the first contributory lectures will be on self-assembled core shell TiO2 ZNE photo anodes for solar cell applications. The second the lecture is on effect of doping concentration on the properties of aluminum doped zinc oxide nanostructures as photo anodes for dye synthesized solar cells. The third one is effects of CO, copper oxide, Al2O3, MnO, and Z2O on a thermoelectric power factor of NBSR TiO3 nanostructures. So these are the 3 contributory lectures which we are going to have. Before that, we will be having the 2 lectures. One is on thematic talk by Professor Ikeda, and the second one will be given by Professor Ganesh D. Sharma. So with this information, I like to introduce our chair of this today's session, that is Professor Madhu Bhaskaran. So I am very, very happy to introduce the chair of this session, and her research interests are thin films, synthesis and characterization, microfabrication, electronic devices, flexible devices, stretchable electronics, and in 2-dimensional materials, it goes to elemental semiconductors and oxides. So to her credit, she has many awards. APEC Science Prize for Innovation.
I don't think you need to read each of those awards. It's okay. That's fine.
Okay, madam has a very long CV. So with that brief introduction, I welcome the chairperson of this session, and I hand over this session to madam.
Thank you very much, Dr. Hariharan, and thank you for having me to chair this session. So as indicated, we'll start off first with the thematic lecture for this session. And that thematic lecture in this case is given by Professor Ikeda, who is from Japan. And as you can see on the slide over there, Professor has a wide interest, especially in semiconductor engineering, in thermoelectric properties and thermoelectric materials. He's also won numerous awards, some of them being listed over there. Among them are the Inter Academia 2018 Young Researchers Award, a couple of Dean's Awards, and also the Inter Academia 2017 Young Researchers Award. So I'll hand it over to Professor Ikeda to start with this thematic lecture. So Professor, you have 30 minutes for this lecture, followed by 5 minutes for questions.
Okay, thank you very much. Thank you very much for the kind introduction for Professor Bhaskaran. Can I share my... Can you see my slide?
Yes, it's very good. Thank you.
Okay. Today, I'd like to talk about the thermoelectric phenomenon related to the electron-phonon interaction using silicon micro nanostructures. Firstly, I'd like to express my thanks for my collaborators and financial support. And this is my content of my talk. Firstly, I briefly explain the electron-phonon interaction in the thermoelectrics mainly. And the next chapter, title of Seebeck coefficient in silicon nanostructure. This is the main body of my talk today. So in this section, I will show the Seebeck coefficient about ultra-thin SOI layers and the phonon drag effect in silicon wires. And the next, if I have enough time, I will explain the case of silicon germanium. And finally, I summarize my talk. Sorry, I cannot go next slide.
Maybe you could stop sharing and try sharing again. That might fix the problem.
no key acts now. Okay. Uh, Firstly, I explained the nanostructures in, electron behaviors in nanostructures such as a quantum well, quantum wire, and quantum dots. As you know, in these nanostructures, there is some effects such as confinement effects, which lead to the discrete energy levels of electrons, and the drastically change in the density of state distribution, and the tunneling phenomenon and the Coulomb blockade phenomenon. Based on these effects and phenomenon, we can improve the device efficiency or create a novel functional devices, such as a quantum cascade laser, flash memory, and single electron transistors. なんで I cannot go next slide. Okay. And electron transport in the nanostructures, as you know, for creating the novel functional device and for designing the high performance device, it's essential to understand the electron transport in the nanostructures. And I think the electron-phonon interaction is one of the important factor of electron transport, because this interaction is deeply related to the energy and momentum dissipation of carriers. And in the present paper, I will focus on the electron-phonon interaction in thermoelectric field. なんでかな
Professor, do you want to try converting the slides into a PDF and then maybe sharing the PDF? It might work. I don't know. I'm just suggesting.
Thank you.
Or else, can you share the PPT so that we can project? So that is also.
Yeah, if you could email the PowerPoint to one of them, if you could maybe let them know where to email it, then they might be able to share while you advance. They can advance the slides for you.
Can you see my slide?
Yes, Professor.
Yes, we can.
Thank you. And And about thermoelectric parameters, here I will talk about the Seebeck coefficient mainly. This is make a role of transfer from temperature gradient to the electric power. And one more important parameter is the thermal conductivity of the materials. This determines the amount of the heat flow. And in the field of thermoelectrics, introduction of non-structure is very expected because it will enhance the Seebeck coefficient due to the drastic change of the density of states and make a reduction of thermal conductivity by enhancing the boundary scattering of phonon transport. Here, I will explain briefly the concept of Seebeck effect. This figure shows a semiconductor, including some carriers. This black point is, for example, electrons. And if we apply the temperature gradient like this, the electrons, velocity of the electron is in the higher temperature region is higher than the lower temperature region. So the net flow of carrier occurs from the high temperature to low temperature region. And after that, the lower temperature region is charged negatively. So there is a built-in potential like this. So finally, the velocity of the carrier flow is balanced. This is a thermoelectric motive force. And this is a carrier, but as well as the carrier, there is phonon distribution is changed. So in the phonon distribution under the temperature gradient, phonon also transports from the high temperature region to the low temperature region. And during the transport, phonon is scattered by electron like this. At this time, the phonon transfers its momentum to electron system. So this phenomenon is enhancement in the electric field. So we call this phonon drag phenomenon. And this contributes to the Seebeck coefficient also. Here, I show the Seebeck coefficient of silicon as a function of carrier density. Please look at the blue plots and lines. These blue plots are the experimental results of the Seebeck coefficient of silicon, bulk silicon, and a solid line of a blue solid line means the calculation of the Seebeck coefficient of electric carrier components here. So you can see the difference between the experimental value and the theoretical value. So this difference corresponds to the phonon drag component in the Seebeck coefficient. And in this graph, the results for the silicon germanium also plotted like this. And you can see that the silicon case, the phonon drag component is much larger than the silicon germanium and germanium case. So that we focus on the silicon for investigating the phonon drag effect. So the purpose of this study, we have investigated the electron-phonon interaction from the viewpoint of phonon drag effect observed in Seebeck effect. So we fabricate the ultra-thin silicon layers and silicon micro nanowires using a silicon on insulator warehouse. We call this SOI warehouse. And after that, we characterize their Seebeck coefficient and discussing about the dimension dependence. So firstly, I will talk about the seabed coefficient in ultra-thin silicon layers. This is a schematic of the SOI layer, and in our experiment, we use the SOI layer with a thickness of 6 to 100 nanometer. And we check the dependency of the carrier concentration. So in our case, the phosphorus concentration is changed to 10 to the 7. Sorry. This is a SOI layer of our samples. And thickness, SOI layer thickness is 6 to 100 nanometer. And we check the dependency of the phosphorus concentration so that we make a variety of concentration materials with 10 to the 17th to 10 to the 20th per cubic centimeter. For measurement the seabed coefficient, we put a sample like a bridge on the heaters, and we apply the temperature gradient from the through the heater, and we check the temperature and the thermal electromotive force and their time evolution we measured. This is a typical data of the seabed coefficient as a function of average temperature. Increase means during the temperature increasing, we obtained data, and decrease is in birth. So you can see the seabed coefficients obtained during the increasing and decreasing temperature are identical like this. So our measurement is valid and accurate. And in this graph, the seabed coefficient is nearly constant in this temperature range. So we replot these data of thermal electromotive force as a function of temperature difference. So this graph has a linear relation like this. From the gradient of this graph, we get the average seabed coefficient in this temperature range. This is a summary of the seabed coefficient for our samples as a function of carrier concentration. The red symbol is the SOI layer data obtained by our experiments. And this number is the thickness of SOI layer. So firstly, you can see peak around the 5 times 10 to the 19th around here. Now we have concluded the origin of this peak is the influence of the impurity band by heavy doped silicon. And here I want to focus on here. The very ultra thin SOI layers has a seabed coefficient very similar to the bulk silicon like this. And this green line is a calculation for the electronic part of the seabed coefficient. So this difference is corresponds to the phonon drag part. From this graph, we calculate the phonon seabed coefficient phonon drag part here. And below the carrier concentration of about 10 to the 18th, it is nearly constant, but with increasing the carrier concentration, the phonon drag component gradually decrease like this. The Seebeck coefficient is usually expressed by this formula. The first term corresponds to the electronic part, and the second part term corresponds to the phonon drag part. And in this part, LPH, this means the mean free path of the phonon, and K7 and K6, these are the parameter integral. This is defined by this equation and includes the mu I, electron mobility due to impurity scattering. So these parameters depends on the carrier concentration or impurity concentration. So we calculate these values as a function of carrier concentration. K7 over K6 value is not so changed by the carrier concentration, but a mean free path of the phonon is a very similar tendency as a phonon drag component in Seebeck coefficient. So we conclude that the phonon drag component is mainly ruled by the mean free path of phonon. So the mean free path should be determined by the scattering rate, so that we calculate each component of the scattering rates. In this case, we calculate the phonon-phonon scattering, phonon boundary scattering, and the phonon impurity scattering. And in these three scattering components, only the impurity scattering depends on the impurity concentration. And in our calculation, the total phonon scattering rate is nearly constant, but around 10 to the little bit increased. This is due to the impurity scattering rate. Impurity scattering becomes significant. So we compare the fitting, the experimental result and the calculation results. Qualitatively, these are agreement with the experimental and calculation results, but quantitatively, there is a discrepancy like this. I don't know now the reason why this discrepancy, but we consider this is influence of the impurity band. Okay, let's go to the phonon drag effect in the silicon wires. Here, I show the silicon wire. Its thickness is 80 nanometer, and the width is 200 nanometer. In this case, the Seebeck coefficient is decreased comparing with ultra-thin SOI layer. And the reported values of silicon wires are very similar, near to close to the calculation result of the electronic part. So we consider that the phonon drag component in Seebeck coefficient decreased with decreasing the width of the wire. This is due to the boundary scattering of phonons. So we calculate again the scattering rate for the phonon-phonon scattering and phonon boundary scattering. In our from our calculation, the when the cross-sectional area of the wire is less than the 1 square micrometer, the boundary scattering component becomes dominant like this. So we make many samples of wires for checking these regions. In our samples, the SOI layer width has a 0.5 to 600 micrometer, and the thickness is 30 nanometer. This is fixed. So the cross-section area is around here. And this is a summary of the Seebeck coefficient as a function of cross-sectional area. So we can get a tendency of decreasing the Seebeck coefficient below the cross-sectional area of about 0.2 square micrometer. This is a good agreement with the calculated expectation. But totally, in our result, there is a discrepancy because the Seebeck coefficient is preserved in ultra-thin SOI layer as thin as 10 nanometer. On the other hand, the Seebeck coefficient reduces in silicon wires with a submicrometer width. So for solving this discrepancy, we analyze from a viewpoint of phonon transport, including specularity in a phonon boundary scattering. So from here, I focus on the specularity in the silicon wire. Specularity is how degree is the phonon is scattered at the boundary, specularly scattered at the boundary. And it is expressed by this formula. And specularity depends on the RMS roughness eta and phonon wave number q and incident angle theta. So firstly, we measured the RMS roughness. This is an AFM image of our sample. And from this observation, we estimated the top surface RMS roughness is 0.4 nanometer, very smooth surface. And next,
Professor, 5
yes.
moments.
Okay, thank you. Next, we RMS roughness at the wall. We check the line profiles one by one like this, and checking the RMS roughness on the side of surface. It was about 1.4 nanometer. So our sample has a roughness of 0.4 at the top surface and 1.4 nanometer at the side wall. The next, we check the phonon wave number by using a Monte Carlo simulation of the electron transport under the electric field of 5 volts per meter. In this case, we count the phonon scattering in the electron transport and make a histogram as a function of phonon wave number contributing to the electron phonon scattering. From this result, about 0.7 times 10 to the 7th Kaiser phonon mainly contributes to the electron phonon scattering.
Madam, Anbu madam.
Okay, and we calculate the specular by assuming the cosine theta equal 1. And at the top surface, the specularity is red line as a function of phonon wave number, and the blue line is for the side wall. And the wave number of phonon contributing to the phonon drag is around here. So the specularity is at the top surface is 0.73, and at the side wall, the specularity is 0.02. And we calculate the mean free time of the phonon. So at the thickness case, the thickness of the material is not so influence to the mean free time comparing with the width. This result also qualitatively consistent with the experimental data, but discrepancy in the discrepancy in the value around here. So finally, I summarize my talk. We investigate the Seebeck coefficient of silicon by focusing on the specularity in phonon boundary scattering. And boundary scattering at the top surface is much less than effective than the sidewall surface for phonons contributing to the phonon drag. So this means that the if we make a quite smooth surface, even if the nanostructure, the phonon drag component in the Seebeck coefficient is preserved. So it is very important information for enhancing the thermoelectric efficiency. Thank you for your kind attention.
Thank you very much, Professor. I invite anyone who has questions to post questions on the chat. But in the meantime, maybe I will start off by asking one question. So in your presentation, you showed that there's very different kind of Seebeck coefficients, or what you're measuring for a silicon material is different to what you're measuring for a nanowire. So, and you've indicated that, wire surface roughness is an important parameter.
Yes.
How do you actually, do you have ideas on how you can actually improve the wire surface roughness so that you can actually preserve the Seebeck coefficient?
Yes. I think top surface is usually very smooth, because usually we fabricate, when we fabricate silicon wires, we use SiO2, making a SiO2 layer and etching by HF solution. So it's a very smooth, but main part is a sidewall. I think this is depends on the lithography and etching materials. So I hope the we can find out the good condition of the patterning. It's
so
very important.
Currently, how you're etching the wire, is that by wet etching or by dry etching?
Now wet etching now.
Okay. Does anyone else have any questions? Feel free to post them there, or if, there's one question from Eben Abraham. The person's asked if grain boundaries contribute to the effect of phonon scattering in your study. Professor, did you hear that question?
No, sorry, again, please.
The question is, do grain boundaries contribute to the effect of phonon scattering in your study?
Clean surface is contributing
no, so if you have grain boundaries, does that also influence the phonon scattering?
Sorry, green boundary.
Grain boundary, yes.
Grain boundary. Okay, grain boundary. Yes. In maybe, of course, it depends on the grain size, because if the grain size is very small case, now the phonon wave number contributing to the phonon drag is a very long wavelength. So I think it's not so influenced by the domains. And if there is a very large domain, it looks like a single crystal, so it's very good. So I think middle point of the grain size is comparing with compared with the wave number of phonon is effective to the scattering. I think so.
So thank you, Professor. There is another question from Keshav. Keshav?
Yeah.
You can ask your question now.
Yeah, actually, I have one question. You are talking about these phonon scattering just affect the your CV coefficient. Have you correlated with this lattice thermal just conductivity? And do you know okay, how it's affected to the electrical conductivity? Because you just showing the CV coefficient is changing through these phonon drag.
Yes, yes,
So,
yes. Okay. Now, today I explain only a Seebeck coefficient and mainly focus on the boundary scattering. So in this case, just a phonon boundary scattering. So this is not so influenced to the electric current. And in the thermal conductivity case, here, usually the thermal conductivity, the phonon wave number contributing to the thermal conductivity is higher. So this is different from the phonon drag. So the usually silicon germanium alloy, it is good for lowering the thermal conductivity, but it is not influences to the phonon drag. So I think the wave number is different from the contributing to phonon drag and thermal conductivity. So we can control the enhancement of these parameters independently.
okay, yeah. Actually, the same phenomena I have got in my samples with the dysprosium filled materials. So the
What
is
material? Sorry.
dysprosium filled scotadites.
Scotlandite.
Scotadites.
Yeah, Scotlandite.
Yeah. Yeah. So I have tried with these just iron doped sample with the just dysprosium field. It's a very newly just materials. So where I just found that the Seebeck coefficient increases with this same phonon drag effect, but I found very low electrical conductivity with those samples. Yeah. So that's why just I need to ask.
How much is the carrier concentration in your sample?
Yeah. It's just
I
around to the 19 to 20 between the 19 to 20. It's the
20.
it's the p-type materials. Yeah.
So I think electrical conductivity, as you know, strongly depends on not only a carrier concentration, but also effective mass of the carrier.
Yeah.
So I think Scutellite, I don't know the Scutellite deeply. So imagine these parameters influences to your case.
Okay, thank you. Yeah. Okay, thank you.
Thank you, Professor. I'll thank you again for your presentation, and we'll move on to the next talk.
Thank you very much.
Thank you. So the next presentation is an invited lecture by Professor Ganesh Sharma from LNMIIT in Jaipur. Are you online?
Yeah, I'm online.
Thank you.
Hey.
Professor will be giving a presentation on recent advances in the organic solar cells based on non-fullerene small molecule acceptors. So I'll maybe allow you to share your screen and then get started. Thank you.
Is it visible to all of you? Is it visible?
Yes, it is.
Yeah.
Yes, it is.
Okay. I'll be talking about the recent advance in the organic solar cell based on the non-fullerene. I'll start some materials, design, and device optimization. Okay, this is the photovoltaic technology, the technology which convert the photons or solar energy into the electrical energy, and that the phenomena is called as photovoltaic phenomena. Now, I just start what is the principle of a solar cell. Solar cell consists of a transparent conducting electrode. Then you have a donor here. Then you have a acceptor here. Then you have a metal electrode. Donor is a p-type material and acceptor is a n-type material. Why we are calling it donor? Because it is donating the electrons and this acceptor is accepting the electron. That's why we call it as a acceptor and the donor. And this is the active layer here. That is the combination of acceptor and donor. This is your transparent container. From here we incident the light and the excitons are created. Then the excitons are diffused toward the interface here, which is built up here, and then electrons are going in these directions, and the holes are coming toward these directions, and the electron and holes are collected by the respective electrodes by the metal and the transparent conductor, and then go to the external circuit and generate the photocurrent. Now this is the once we fabricate the device, first we have to check that whether our device is formed or not. For that, we have to do the experiment of dark current voltage characteristics. If you are getting like this is the dark. Once we illuminate the light, then this is your short circuit current. This is your VOC voltage, open circuit voltage. This is the maximum power. This is the maximum power point, and this is given by this power conversion efficiency is JSC, VOC, FF is fill factor upon incident light. And this is the fill factor here. This fill factor is very important for a high efficient solar cell. This must be equal to 1, but in generally this value is less than 1 due to some losses. Now photovoltaic technology, first it comes into the conventional silicon solar cell. The efficiency was about 16% commercial application, and at laboratory scale it is 26%. And then the thin film technology came to account using the thin film crystalline silicon and other inorganic semiconductors. The efficiency was about 16% at laboratory scale and the 10% at commercial scale. But there are some limitations of these materials, that is high cost, large area fabrications, and the less flexibility. But for that, then the people started to work to reduce the cost of the solar cell, and there is a search for new materials, that is organic materials, perovskite and quantum dots, etc. So I'll be talking about the organic solar cell only. These are the ideal requirement for a solar cell. That is, the materials which we are using, that should be cheap, simple, abundant materials in nature, minimum material per watt, but that is cost, and low production by optimizing the material and fabrication technology. And we should get the high power efficiency for a solar cell. Now, these are the suitable electronic and optoelectronic properties, that is the materials which we are using in the active layer. Active means combination of P or N or donor acceptor should have high absorption coefficient, as well as they have the broad absorption spectra covering the UV visible and then near IR. And the materials which we are using in a solar cell in terms of donor acceptance, they should form the junction. That is, first of all, we have to fabricate the PN junction. So this is called as a suitable energy levels. The energy levels should be suitable so that the P and N type semiconductor should form a junction. High quantum efficiency means every photons which are incidenting on the active layer should generate the current. So this is called as a high quantum efficiency. This is your solar spectrum. It's covered from 300 to up to 1100 nanometers maximum photon flux. Now, this is the case for an inorganic semiconductor. This is the case for the organic semiconductor. In organic semiconductor, just like silicon, germanium, and other inorganic semiconductor, you have conduction band, you have valence band separated by the band gap. Whereas in the case of organic semiconductors, these are the LUMO levels here. These are called as LUMO orbitals. These are called as HOMO orbital. That is lowest unoccupied molecular orbital. This is called as highest occupied molecular orbitals. Okay, this LUMO, this is just like conduction band. This is just like a valence band. All the orbitals are occupied here. All the orbitals here are unoccupied. Though you can compare, we can say that this LUMO is just analog to the conduction band here. This HOMO is just like the valence band here. So now, once we make the device, for the material design, that is, in the case, all the materials can be designed for in the form of donor acceptor combinations. These are all the monomers units are called a donor unit. They have the different electron donating capability. These all are have the acceptors which have the different electron accepting ability. So if you want to make a molecule, we can combine this and this, we can combine this and this, we can combine this and this. So we can, there is a lot of flexibility to design the number of lot of number of small molecules or polymers. Now you can say that this is your donor here, maybe from this one, any of them. This is your acceptor here. Okay. Now when these two molecules these two monomers combine each other, so there is a intra-charge transfer between donor and acceptor, and this will form a DA molecule like this. So now by tailoring, so this is your DA molecule. So now the band gap has been reduced. Here band gap is this, here band gap is this. Once these two molecules, maybe this and this, maybe this and this, and we can design lot of DA molecules or DA polymers. D means donor component and A means acceptor components. So these are all the, so we can, so now the energy levels, you can see here, this energy levels and this energy level can be tuned with the help of different type of donor and different type of acceptors. So we can make different type of molecules or polymers ranging from narrow band gap to wide band gap. It is needed that sometimes we need wide band gap semiconductors, or sometimes we need narrow band gap semiconductors. So by using the different types of monomers, we can design different types of DA molecules or DA polymers. Now there are different types of now the band gap can be tailored by different effect of band, this one, I have written here, this donor level, the HOMO level is responsible, or you can decide by the donor component. Similarly, the LUMO level of the DA molecule or polymer can be decided by the acceptor here. So by tailoring the capability of donor and acceptors, we can design different type of molecules and polymers. So these, or you can say that there's a different type of conjugation shell. If you could change the conjugation length, it will also affect the band gap. And if you put something here, this will lead to increase the solubility of the material, because in organic electronics or organic photovoltaic, we always use solution processing technique to design the or to fabricate the device. So you can say, I just taken this is one, this is the weak donor here, and this is your weak acceptor here. So we can weak donor and strong acceptor molecule like this, or you can make again the polymer also. Now I'll just take the, now what is the basic difference between organic solar cells and a inorganic solar? As light is incident from the transparent conducting electrode and light is absorbed by the active layer. The active layer is consist of donor and acceptor, that is PN junction. Once the light is incident in organic semiconductor, excitons are generated, but the exciton binding energy is very, very low, in the range of 0.025. So 0.025 energy they can take from the thermal energy, that is equivalent to that. So as soon as the excitons are formed, they will dissociate into free charge carrier. But in the case of organic semiconductors, due to the low dielectric constant, so you have this low dielectric constant in the range of 3 to 10, whereas here it is maybe 50 to 100 dielectric constant. So here, because due to this low dielectric constant, the excitons binding energy is in the range of, I'll just write EB here, is equal to 0.3 electron volt, like this. So now, once the excitons are generated here, they are not free. So you need some external driving force to dissociate these excitons into free charge carriers. So for that, we have to create the internal built-in electric field so that they can be dissociated in free charge carrier. A second thing is the diffusion length is in the range of 10 to 20 nanometer here. That means the excitons which are generated, they should dissociate into free charge carrier before they collapse. So these are the some disadvantage of the organic semiconductors. Now, in the early stage, the organic solar cells are made using two layers. This is N-type, this is P. First, this is transparent conducting electrode. This is your P-type material. This is N-type material, and the excitons and the junctions is here. So when the incident light here, the excitons can be generated here, and then they will move here, and then electrons will go there, and then so this built-in electron field will dissociate the excitons into free charge carriers. Then you have this is your anode here, this is your cathode here. Then the electrons are going here, then they will move here. Then the holes are like this. So now the holes are moving through the HOMO level of the materials and collected at anode. Similarly, the electrons are moving toward the cathode through the HOMO level of the LUMO level of the materials. So this is the mechanism here in the two-layer system. Now because this is your P, this is your N, I can just write here. Okay. Now when the light incident, only the excitons which are generated here will be able to dissociate into free charge carriers. Similarly, and the excitons which are here, generated here, they will be not able to reach to the interfaces because due to the low exciton diffusion length in the region. So it means only the excitons which are generated here, they are reaching to the interface and they will contribute to the free charge carriers. And these are lost. So the current is very, very small in this case. So this is the limiting factor of the two-layer system. After that, a Professor Higger in 1991 developed a concept. Instead of making two-layer systems, why not we mix the P-type semiconductor and N-type semiconductor in a common solvent and then make the print? So that concept is called as bulk heterojunction solar cell. It was developed in 1991, and due to this bulk interface, there are a lot of interfaces here. All instead of one PN junction in the two-layer system, there are many PN junctions formed in the active layers. So wherever the light incident, excitons are generated, they will find a near interface, near DA interface. And they will dissociate free charge carriers. So this is the, and or you can say that the interfacial layer has been increased in the case of bulk heterojunction concept. After that, the people started to work on the bulk heterojunction solar cells. Now, what is the concept here? That is, it is now I will talk about the bulk heterojunction. The bulk heterojunction active layer is sandwiched between two electrodes. That is your anode here, cathode here. So once the light is incident, what happens? First process is that excitons are generated. And the number of excitons generated in the active layer depends upon the absorption profile of the active layer, the combination of P and N-type material. Once the excitons are generated, they will dissociate into free charge carrier. And that is called as, and this is called as a exciton dissociation. Once the free electrons and holes are created, then they have to move into the different directions. That is depends upon the phase separation between donor and acceptor material. That is called a, and then that should be optimized. So these are the process here. Absorption here, exciton dissociation, then charge transfer, then charge collection. Okay. Now, once the electron and hole pairs are, now the electrons will move toward the one direction and hole will move in the different other direction. So now the main thing is that the electron mobility, that is mu E and mu H, are comparable. Or you can say the mu E upon mu H must be equal to 1. Otherwise, if it is not this, otherwise what happens? The electrons, suppose the electron have higher mobility and hole have less mobility, then the electrons will be collected very fast and holes will accumulate at the interface, and this is called a space transformation. So we have to optimize the nanoscale morphology in such a way that the electron and holes should reach to the respective electrodes at the same time. For that, this should be needed. Now, so we have polymers, we have small molecules, fluorine and non-fluorine. Okay, fluorine is the acceptor. This is your donor. This can be donor and acceptor. Okay, so we can make solar cell using polymer fluorine. So this is called a polymer fluorine solar cells. If you make this one, we can say that all small organic solar cells. If you take this one and this one, this is called polymer fluorine, non-fluorine solar cells. Now I just discussed. Now this is your repeat and this is your donor here, the acceptor. So this is the driving force for exciton dissociation. This should be this is called a LUMO offset. This LUMO offset should be greater than 0.3 electron volt. That is exciton binding energy. Okay. If it is less than that, then excitons will not dissociate it and there will be no charge transfer. So it is needed that this LUMO offset should be greater than this one. Or if you want to reduce it, we have to use donor or acceptor with high dielectric constant so that the excitons binding energy can be reduced. There are different there are different types of solar cell can be used for the organic solar cell. That is called a conventional. You have a anode, then you have a donor acceptor like this. This is your inverted. Just this is okay. Now, in the early stages of the organic solar cells, the solar cells are based on polymer donor and fluorine here, and the efficiency was about 12%. But there are some limitations of this fluorine derivatives, that is high electron affinity. These are the advantage of the fluorine, but these are the disadvantage. That is, it has high cost, it has limited absorption spectra, up to it absorbs up to only 650 nanometers, and it is difficult to design or to tailor the HOMO level and LUMO level. It is difficult to tailor the HOMO level and LUMO level of the fluorine derivative. And there is another drawback, that is energy loss. Energy loss is in this case is in the range of 0.7 to 0.8 electron volt, which is a drawback to get high voltage. Because the voltage, this is the open circuit voltage, if it is high, the open circuit voltage will reduce. So we have to optimize the energy loss or voltage loss in a solar cell so that we can increase the efficiency or increase the open circuit voltage. Now, this is the advantage of these are non-fluorine. Non-fluorine solar cells are based on small molecule. They have the strong absorption coefficient, small energy loss, improved morphology, better stability than the fluorine-based solar cells, and they can be used as a ternary blend also. these are the absorption can be increased, energy level can be changed, geometry can be changed, and morphology can be changed by the using of non-fluorine acceptors. This is not possible in the case of fluorine PC70BN or PC61BN like this. Okay. Now, in the early stage, the non-fluorine solar cells, that is perylene is used, but and the efficiency was about only 4.1%, and it absorbed the light only from 300 to 600 nanometers. Okay. And these are the different types of this. You can tailor it here. This is two. This is dimer. This is dimer here. This is dimer here. And the efficiency, maximum efficiency was achieved in using the PDI dimers, acceptor, and polymer as a donor, and the efficiency was about 7.1% efficiency. Most of the PDI absorb light from 300 to 600 nanometers, and band gap is around 1.9 electron volt, which is just like the PCBM, and the mobility is like this. And then after that, the people started to work on a different type of non-fluorine acceptor. This is consist of a D molecules, or you can write also D or ADA. Also this. Okay. So this started in 2013. And because this is DAD, so we can choose different type of acceptor, different type of donors, as I have discussed in my earlier slides. We can choose donor from that table, and they can be used also for a transparent. So first of all, in the 1913, first non-fluorine acceptor was developed. This is your donor here, this is your A and D here, A here. And this is your pi spacer. So we can change this one, we can change this one, we can change this one. So we can tailor the property of the non-fluorine easily. So we can make wide band gap non-fluorine acceptors, we can make medium band gap non-fluorine acceptors, we can make narrow band gap. When we use a wide band gap polymer donor or small molecule donor, we have to use a narrow band gap non-fluorine acceptors, so that the absorption profile can be increased from 300 to up to 900 or 10 or 1000 nanometers.
Professor, sorry to interrupt.
Sorry?
Another 5 minutes.
Okay, okay. This is your accepted non-fluorine acceptor here, and the efficiency was about 3%. After that, this is your again non-fluorine acceptor donor here, acceptor here, donor here, and this is your another type of acceptor. The efficiency was about, and we have achieved in one experiment, we have achieved this one 6.3%. And again, you can see in there's another group who have changed slightly the non-fluorine acceptor. They got efficiency about this one. We got this 6 point, but they have changed the something here, and they got efficiency about 11.10%. This is another case. They in 2017, 13% was reported. This is the our God. We have done something. They are non-fluorine acceptors. We got about 18.3% efficiency that were published in 2016. This is again another type of acceptors here, donor acceptors. And the maximum efficiency we got about this one. This is again this is acceptor here. This is acceptor here. This is your donor here. So we got efficiency about 7 point something. And there is another, this one again a small molecule here. This is donor here. We got efficiency about 9.2% efficiency. This is again, now the maximum efficiency was reported earlier is 16% using this is your non-fluorine acceptors, and the in a Chinese group they had developed another type of non-Fourier acceptor, Y denoted as Y16. They got efficiency about 15.7% efficiency. After that, the people started to work on Y16 series, modifying this is your 1 unit here, 1 unit here, 1 unit here. So you can modify this, we can modify this, we can modify this. They can make, and the many type of non-Fourier acceptor can be designed. Now, recently in 2020, 18% efficiency was reported using this acceptor, non-Fourier acceptors, and they have used a wide bandgap acceptor donor here. Recently, 18% efficiency was achieved. This is again, you can see this is your Y16, and this is the donor here, polymer donor here, and efficiency was about 18% reported so far. Now, there is some limitations which I have discussed only up to that is DA, or it is called a binary system. Only binary system. Now, if you want to increase the absorption profile, we can use one donor, two donors. One donor here, two donor here, one acceptor. This one. So this is called a ternary system. So in the ternary system, either we can use two donor, one acceptor with complementary absorption spectra, as well as we have to see that their energy levels or HOMO level or HOMO and LUMO levels are compatible or not. So this has to be taken into account. And there are different types of mechanisms. There charge transfer can be taken, may take, energy transfer may take. This is the parallel linkage here. So there are different types of mechanisms in the ternary system using either two donor, one acceptors. So you can see here, electrons here, hole here, electrons here, hole here. And earlier the efficiency was, and we have also designed some, this is donor here, acceptor here, acceptor here. So we got efficiency about around 10% efficiency that was reported in 2018. Similarly, we have used a ternary system using a PCBM is a don't acceptor. This is another acceptor here, non-Fourier acceptors. We got efficiency about 9.6% efficiency. And recently, the 20% efficiency has been reported for indoor applications. And there is another, this is the tandem solar cell, using tandem solar, one cell here, one cell here, but this is a complicated process, and the efficiency was reported about 18% efficiency recently. This is the tandem solar cell that is reported 17.3% efficiency. They're using two. This is your one cell here, one cell here, and this is it is an intermediate layer. Now, how can you fabricate it? This is a simple fabrication technique that is done by using the Doppler plate technique. We can make the different types of solar cells using the organic solar cells. This is one of the panel here. It is 9 centimeter by 9 centimeter. They have reported the 10.8% efficiency for this area of this one. Using this is your donor here, acceptor here. This is your donor here. So this is again using. So we have also developed a panel here with the help of Russia, and the efficiency was about 8.3% efficiency with 12 centimeter into 12 centimeters like this. Here like this. So recently the 18% PEC has been achieved for the using a solar cell using non-Fourier acceptor. This you can put it here. Now this is started in 1991. Now the efficiency was about 18% efficiency, and the key factor is that the energy loss should be reduced using the different types of molecule, different type of organic materials with high dielectric constant, so that the binding energy can be reduced. And once the binding energy can be reduced, we can increase or can decrease the energy loss and increase the open circuit voltage. Now, up to now, the 1.5 volt has been achieved open circuit voltage, and it is maximum efficiency about now 17% like this. These are the things. But now we are working on the transparent organic solar cells so that these can be used, or you can design the new material with a high dielectric constant, reduce the binding energy, that exciton dissociation can be increased so that you can increase the photocurrent as well as the open circuit voltage. This is the case. So these are my collaborators with Indian and abroad. We have the collaboration with Spain, Israel, Spain, France, and this Canada, like this. Thank you very much.
Thank you very much, Professor. In the interest of time, we'll maybe just do one question. So, Justin, I think you had a question.
Hello, Professor.
Yeah.
Thank you for a nice talk. My question is why the non-fluorine-based acceptors exhibit high stability in bulk heterojunction solar cells compared to fluorine acceptors?
What happened? The fluorine are not a photostable materials.
Okay.
And this non-fluorine acceptors are much better, have much better photostability.
Okay. So how long the solar cells are stable without encapsulation?
It is maybe around, we have checked it, it is up to 6 months.
Okay. Thank you. Thank you.
Thank you very much, Prof.
Right now, the fluorine is almost obsolete because the non-fluorine are they are very cheap. They can design in the laboratory, or we can change the energy levels, also the absorption profile according to our requirement. What happens once we use a wide band gap donor, maybe polymer or small molecule, we have to use a complementary absorption spectra. So we can, for a non-fluorine, we can design the wide band gap also, we can narrow band gap and the medium band gap. This is a flexibility with the non-fluorine acceptor.
Thank you, Professor Sharma. Thank you again for your presentation. In the interest of time, we'll move on at this stage to the 3 contributed presentations. So there are 3 presentations which are contributed. A reminder, each of these are only 10 minutes. So the presenter has 8 minutes to present, followed by 2 minutes of questions. Is the first speaker ready? So that's a presentation on self-assembled core shell titanium dioxide zinc selenide photoanodes by Kulandai Velu Ramanathan from Amrita Vishwa Vidyapeetham in Kochi. Thank you very much. Over to you.
Good afternoon to everyone. I'm Kulandai Velu Ramanathan. I'm from Amrita Center for Nanosciences. So today we are going to talk about self-assembled core shell TiO2 zinc selenide photoanodes for solar cell applications. So there are 3 types of solar cells actually in the field, and we all know that the first generation solar cells are bulk silicon based solar cells. The second generation are the thin film solar cell, which is like cadmium telluride, CIGS, and etc. The third generation of solar cell includes the DSSC quantum dot sensitized solar cell, which are called excitonic solar cells. Here, I'm going to talk about excitonic solar cell first. So, in an excitonic solar cell, we always use a material to transport the TiO2, to transport the charge carriers, and we use a separate sensitizer for charge like for exciton generations. So here I have chosen a core shell particle to actually do the same. The shell of the particle is going to be a photo absorber in my case, and the core of the particle is going to be the photo like anode of the device. So why we use core shell particles? It actually improves the exciton generation, and it also helps in the charge transport properties. So here I have used zinc selenium as the core, as the shell of the particle, and TiO2 as the core of the material. So zinc selenium has a band gap of 2.3 electron volt, which actually shows that it has a very good photo absorption region in the visible spectrum. And it is also used as a shell in many quantum dot sensitized solar cells like cadmium selenide, cadmium sulfide, and it is prevalent in the literature. So the TiO2 is a wide bandgap material, and it is mostly used in all third generation solar cell as the anode material. And here we used TiO2 nanoparticles as a seed layer, and on which we coated zinc selenium. So, so first I'll go through like how we made the zinc selenium TiO2 quantum like core shell particles. So first we took TiO2 nanoparticles and dissolved it in water, and we added a zinc salt, zinc acetate to be precise, on top of the TiO2 to get an ionic solution which has zinc plus ion, zinc 2 plus ions. And in a separate beaker, we actually added sodium selenide to form the selenium precursor. Along with it, we used sodium borohydrate as a reducing agent. When the sodium solution, the selenium solution is added to the zinc counterpart, we got zinc selenium, which turned to be that orangish color which you see in the picture. So that formed the TiO2 covered with zinc selenide, and we actually centrifuged the solution to obtain a precipitation. So once the settled powder, we actually dried it at 60-degree vacuum, 60 degrees Celsius in vacuum conditions to obtain the zinc selenium TiO2 core shell particles. So once the powder is obtained, we actually doctor bladed onto a FTO glass, and we use that as a photoanode material. So we took absorption and photoluminescence characteristics of the zinc selenium and TiO2 core shell particles. So as we can see here in the first image, the absorption of the pristine zinc selenium is actually started absorbing from the region of 800 nanometers to 300 nanometers in a exponential way. But when we are actually making core shell particle with TiO2, we can see that the particle actually, the absorption is more like an even rather than an exponential way. And we can also see that there is a difference according to with respect to the presence of TiO2. We can see the difference in the photoluminescence as well. So the pristine zinc selenide actually has a less intensity, and it shows the photoluminescence of zinc selenide is comparatively less when than the photoluminescence of TiO2 zinc selenide core shell particles. So here we can see the micrographs of TiO2 nanoparticles and TiO2 with zinc selenium core shell particles. So the first set of images shows the clusters of 25 nanometer TiO2 nanoparticles, and the second set of images shows the core shell of TiO2 and zinc selenium particles. So this core shell actually, it formed to be an even particle. It actually covered the TiO2 particles. The zinc selenium covered the TiO2 nanoparticles, and it is like clear that the whole morphology of the TiO2 has been changed, which is not compared to that of the TiO2 nanoparticles in pristine. So yeah, there is a working principle of the electrochemical solar cell. Okay. So first, we actually doctor blade zinc selenium TiO2 core shell particles on top of a FTO, which is a transparent conducting material, and we use polysulfide as an electrolyte. Because of the selenium present in zinc selenide, we cannot use other electrolytes like iodolite or others, and we use copper sulfide as a counter electrode in order to make sure the polysulfide actually transfers the charge carriers into the counter electrode. So first, what happens is, like, when we eliminate the zinc selenium nanoparticles, like zinc selenium TiO2 core shell particles, the exciton generation happens in zinc selenium, and it is actually transferred to the TiO2. And the TiO2 actually, by diffusion method, it actually transfers the electrons to the FTO, and the zinc selenide is actually transferring the holes to the polysulfide, by which it is getting regenerated by the polysulfide electrolyte, which collects the electrons from the copper sulfide and transfers it to the zinc selenide's valence band minimum, valence band maximum, and also it actually collects the holes through the counter electrode. So this is a working principle of a electrochemical solar cell. So here we took a preliminary study of this study material actually, and we made a device out of it, and we can see that the device characteristics actually resembles, we have got a good device characteristics, but it is not an ideal PV characteristic, like ideal diode characteristics, because the zinc selenide is actually absorbing more light. The excitation generation is high in zinc selenide, and it is actually transferring it to the counter electrodes. As we can see that the current density, the short circuit current density is very high, but the voltage of the material is very low. So what is the difference? Why the voltage of the material is very low is because the mismatch in the redox potential and the zinc selenide's valence band minimum, valence band maximum. So we can see that that is the reason that the power max of this device is actually very low compared to the uh, short circuit current density. And so the further study will be actually increasing the efficiency as well as the voltage, open circuit voltage of the device by tuning the polysulfide electrolyte or by changing the properties of the zinc selenide TiO2 core shell particles. Okay, so as we can see here, like the preliminary results show that there is a potential application for photovoltaic devices using TiO2 zinc selenide core shell nanoparticles, and the current density shows that zinc selenide actually collects more, like the more excitons are generated in zinc selenide, and it is injected into the TiO2's conduction band minimum very efficiently, so that we can collect it through the FTO. And the further improvements in TiO2 zinc selenide core shell particles will actually lead us to good for prospective photoactive material. Thank you.
Thank you very much. I'll just open it up for questions. So anyone who has a question, feel free to unmute and ask away. Was there anyone with a question? I might just ask you a quick question. So you indicated you need further improvements to the material, right? So
Yes.
what would be the first thing to try in terms of to improve the material towards, having a better photovoltaic applications?
Okay, like actually here we have tried with different concentrations of the TiO2. We have changed the different concentration of TiO2. But actually, by changing the stoichiometry of the zinc and the selenium precursor, we can actually change its property while the synthesis. So here we have used 2:1 ratio of 2 zinc precursor and 1 is selenium precursor. When we change the stoichiometry, when we get like 1:1 or 3:1, so we will actually change the property of the zinc selenide, which is forming over the TiO2. By that, actually, the whole property will be different.
Right. Thank you. Thanks for that explanation. So I'll maybe move on to the next presentation. So thank you very much, Velu. The next talk is by Neena Bachchan from Loyola College in Chennai, and that's on the effect of doping concentration on properties of aluminum-doped zinc oxide nanoparticles. Neena, if you're there, you could share your screen and start.
Hello, ma'am. Can you hear me?
Yes, I can. Could you share your screen and then you can
sure.
start your presentation?
Yeah, sure. Is my slides visible now?
Yes, I can see your slides. Thank you.
Yeah. Yeah, myself, Neena Bachchan, and today I will be presenting the effect of doping concentration on the properties of aluminum-doped zinc oxide nanoparticles as photoanodes for dye-sensitized solar cells. I've done my work at Loyola College and currently I'm working in Providence College of Engineering. And Before we go to the direct synthesis part, I just want to tell some introduction. Actually, the semiconductor metal oxides have been under extensive investigation due to the wide application in energy storage and environmental remediation. So, recently, ZNO is emerging as an important metal oxide owing to its cheap, abundant raw material, then direct band gap and high transmittance in the visible region and non-toxic nature. For the purpose of improving the electrical conductivity and optical transmittance of ZNO, group 3 elements such as
Nina, we are not able to see your slides. It's still in the main slide. Are you moving your slides?
Okay, ma'am, I move now. So, group 3 elements such as boron, aluminum, gallium, and lithium are introduced into ZNO. So, for my work, I have synthesized the ZNO nanoparticles using the Sol-Gel method. So here, zinc acetate dehydrate is diluted in ethanol and it's stirred for 13 minutes. Then simultaneously we're mixing sodium hydroxide into it, and then after stirring, then the sediment is collected and then it is washed with ethanol, filtered, and it's kept in the furnace, and we have done the calcination.
Very nice, right?
And then we, in order to incorporate the aluminum tops ZNO nanoparticles, we have added aluminum chloride, which is dissolved in distilled water, and according to the we have done it for 3 concentration, like for 1% to 3%, like that. So after doing this, we have altogether 4 samples. One is a bare sample, that is our ZNO sample, and 3 different concentrations of top samples, like 1, 3, and 5. So in order to study the characterization techniques, we have done the powder XRD, and you can see the figure. And for ZNO, you can see that it is a hexagonal wood set structure, and it is well matching with the JCPS card number. Very sharp, which shows the crystallinity of the sample. And you can see as we are increasing the measures of the sample, and there is not much aggregation, and it is all, in all these things, it is clearly distributed. And we can also see a particle size distribution that I have mentioned on the table, and it is decreasing as the concentration of doping is increasing. This is the IDAX, and from the IDAX, I have seen that all the samples were pure, that is only ZNO peaks were there, and in case of doping, we can see the small aluminum peaks, and it is very small as the doping concentrations are very. And here you can see a bar diagram of crystallity for the undoped sample. The crystallized size and particle size is greater, and it is decreasing as the doping concentration is increasing. UV DRS is done, and from the Kubel-Kalman plot, we have seen that the band gap of the sample is different for different samples, and it is highest for undoped and lowest for 1%. And then in order to find the surface area, a bet has been done, and surface area is also varying. So the highest surface area is for 3% aluminum doped ZNO, and the least for undoped sample. Field-dependent dark photoconductivity studies are done because our application of this material is for dye-sensitized solar cells. So actually this field-dependent dark conductivity is a two-probe technique, and in all the diagrams you can see that it's showing an ohmic nature, that is as voltage increases, current is also increasing, and in all the samples the photocurrent is greater than dark current. So what we did is that we have collected all this information. We have collected all this information in order to optimize the sample, because I just wanted to compare the bare and the doped. So the main things I have taken into consideration is the band gap, surface area, and photocurrent. So after seeing this, I have found that the bare sample Z and the 3% dot sample A is Z3 I have chosen as the best samples. I compared it and I've done the IV characterization studies, and we got the efficiency as 0.3 for undocked and 0.48 for 3% top samples. And these are the conclusion. We have followed a simple Solgel method for synthesis of docked and undocked samples, and we have varied the concentration so that the doping concentration will be different. And XRD basic studies like XRD, HRT, things are done, and it has showed that the samples are pure, and the particle size decreased with the aluminum concentration, and the crystalline size also decreased with aluminum concentration. And the band gap of aluminum doped isocyanates was found to be significantly less than that of bare nanoparticles. And from that also we got like a significant influence on the bed surface area due to doping is there. And from the field-dependent darkened photoconductivity studies indicate that there is a linear increase in the current according to the applied field. And from the dop samples, 3% there dop showed the significant conductivity due to its it may be due to its high surface area. And then so from it has been explicitly proved from the IV characteristics that 3% showed improved efficiency than there is the optimization is a 3, that is 3% dot sample. Thank you. And acknowledge Times of India Lala College Research Grant, Lala College and Providence College.
Thank you, Nina. So I'll open it up for questions. So if any of the participants have a question, could you please raise your hand on the Zoom, using the Zoom screen, and we can then pass it on to you to ask your question. Yes, there is one question from Aditya.
Yes, ma'am.
One second. Could you please unmute the person who would like to ask? Thank you.
Yeah, thank you, ma'am. Nina, nice presentation. I have two doubts. First doubt is how you fabricate your photoanode, in which method you have followed to prepare your photoanode?
Yeah, the answer for that is we have used the Dr. Blade method, and we have coated it over the FTO substrate.
Okay.
So yeah, we have coated it over the FTO substrate and using the Dr. Blade method. We have made the sample into a paste and we have coated it. So that's how, and our counter electrode, we have used it as aluminum sheets, and then we have done the IV characteristics, and the dye we have used is black dye.
So which dye you have used for your fabrication method with your device?
We have done, here I have shown it for saffron ore dye.
Okay.
And we have done it for black dye also. And we got more efficiency for that when compared to this.
Okay.
Because this is like a preliminary work. So we just wanted to see whether which sample and which dropping concentration is good for moving the work forward. So we found it at as 3%.
Okay. And one more question. In ZNO alone, based on the literature review, the researcher already attained 4% of efficiency.
Yeah.
So what is the novelty of your work?
So actually, this is, we have done it based on dye-sensitized solar cells.
Okay.
So basically for dye-sensitized solar cells, the efficiency is a little less when compared to other solar cells. And here, the novelty is that the counter electrode we have used is the aluminum other than the platinum. And the synthesis method is also different, and we have done the photoconductivity studies which have not been done by many people, because from photoconductivity studies we can understand about the surface charge movements and all.
Okay. Thank you for your answers.
Thank you, ma'am.
All the best.
Thanks.
Thank you, Nina. Thank you very much for your presentation.
Thank you.
We'll move on to the last presentation for this
I have a question.
session. I'm sorry, but in the interest of time, we're just trying to move on. We're already running behind time. So for those of you who would like to still ask questions, hopefully you can reach out to the speaker directly and then have a conversation. So last presentation for the session is by Charan Prashant on effects of copper oxide, aluminum oxide, manganese oxide, and zinc oxide on thermoelectric power factors. And he's from Central University of Tamil Nadu. So if you're here, Charan, you can make a start.
Good afternoon, ma'am. Can you hear my voice? Hello?
Yes, I can hear you.
Okay. Okay, I'll start this session. I'll start. Can you see my slides?
No, we can't.
Now, could you able to see?
Yes, we can see your slides now.
Okay. My work is on effects of copper oxide, aluminum oxide, and manganese oxide, and zinc oxide added thermal added NB doped phantom titanate. Okay. Now, let me introduce about the thermoelectric materials. Thermoelectric materials are the materials which converts the heat into electricity. In the real world, if you see, for example, in an IC engine, if you take only 30% of the fuel is converted into energy, the rest of the fuel are wasted as heat. So thermoelectric generators are very useful in the waste heat management. Hello, could you able to?
Yes, we can still hear you.
Okay. So the main application is on the waste heat management. The main advantages of thermoelectrics are it has no moving parts, so we can easily use it as a generators. Mostly in space applications, thermoelectric generators are widely used. For example, the radioactive thermoelectric generators are used in the space probes. So here I have chosen the strontium titanate, which is a good thermoelectric material when it is doped with several donors. When strontium titanate is doped with Nb, which gives a good thermoelectric properties. My work is on adding copper oxide, aluminum oxide, and manganese oxide and ZnO as additives, which results in good thermoelectric properties of Nb-doped strontium titanate. Here, the samples are synthesis by conventional solid-state synthesis method, and the XRD spectrum of samples are taken, and the single phase of samples were confirmed. And the electrical conductivity and Seebeck coefficient of the samples are measured simultaneously from 670 Kelvin to 1073 Kelvin. The maximum of 231 Siemens per centimeter is obtained at 550 Kelvin for copper oxide mixed Nb-doped strontium titanate, and maximum of minus 222 microvolt per Kelvin Seebeck coefficient is obtained for MNO doped Nb-doped strontium titanate, and the maximum power factor of 306 meter watt per meter inverse Kelvin inverse was obtained for copper oxide mixed Nb-doped strontium titanate. The densities of the samples were measured by Archimedes principle. here are the brief synthesis, elaborate synthesis method, where the precursors are taken in stoichiometric amount and ground for 12 hours and calcined for 1273 Kelvin, and then the additives are added and pressed into pellet and then sintered at 1623 Kelvin in hydrogen and nitrogen mixed atmosphere in order to reduce the sample. Here are the XRD patterns of the sample, where the peak shifts were observed towards the higher angle, which shows the distortion in the unit cell. Then the electrical conductivity of the samples were measured by Nash instruments, where copper oxide mixed NB-doped strontium titanate showed the higher electrical conductivity, which is 231 Siemens per centimeter. Overall, the electrical conductivity of the samples tend to increase when the temperature increases, which shows the semiconductor behavior. At higher temperature, it tends to decreases, which shows the metallic behavior. Then the Seebeck coefficient, where the higher Seebeck coefficient of minus 94 microvolt per Kelvin was observed for aluminum oxide mixed NB-doped strontium titanate, where the Seebeck coefficient for all the samples, where Seebeck coefficient tend to increase when the temperature increases. So here the power factor for copper oxide mixed samples show the higher power factor comparatively. Among the samples, copper oxide around 306 microwatt meter inverse meter power minus 2 Kelvin power minus 2 was obtained for copper oxide mixed NB-doped strontium titanate. As the power factor depends on the Seebeck coefficient and electrical conductivity.
Sharon? Excuse me.
Hello? Yes. Okay, here the conclusion. So the additive decreased the sintering temperature from 170 to 1723 Kelvin to 1573 Kelvin by acting as a sintering aid. And also Al2O3 copper oxide and MnO added samples showed the better behavior comparing with ZnO. So the additive helped to increase the carrier concentration by creating number of oxygen vacancy, more number of oxygen vacancy in the lattice. Oh, thank you.
Thank you very much, Sharon. Questions from the audience. So if you could raise your hand if you'd like to ask a question. Yes, Keshav. Yes. Keshav Prasad.
Yeah. Hello, Sharon. Yeah.
Yes.
Actually, I have one question. You are saying that the Seebeck coefficient is increasing with increasing in temperature, but you can see if you go with your Seebeck coefficient for particular sample, it start to decrease after certain temperature range. So can you explain that?
What? I didn't get your question. What?
If you go to your Seebeck coefficient data. Yeah, just yes.
Okay.
So yeah, you were saying that for this particular these 750, so you can see that for the initial temperature it start to increase and then decrease. For all the samples it just started to decreasing. So like your data is not showing the like a complete behavior. So it's an instrument error, or you just can explain this?
No.
For the ST.
It's actually we have problem with the instrument in lower temperature.
Hello.
So we couldn't access completely.
Hello. Hello, Charan.
Yeah, we have some problem with the instrument at lower temperature. The contact was very not good at the lower temperature, so we couldn't get reliable reading in the lower temperature. So we neglected the below 700 Kelvin temperature.
Because you can see also that the data is not like something continuous for other sample also for the this one STN gender no. So I don't think so. It's like contact problem, because if the contact problem, so sample will not work to start with the just initial temperature.
No. The thing is, we have problem with lower temperature. I have done the measurement multiple times for the same sample. For higher temperature, it behaved for more than 700 Kelvin, it behaved like the same. But in the lower temperature, it showed the data was very chaotic.
Okay. Just for ask, which instrument you are using for the CBEC measurement?
Nesh.
Okay, Nesh.
Yes.
Okay, you are using the Nesh one. Okay.
Yes.
Okay, good. Are you using the
There's
bar sample? Okay. You are using the bar sample or just a circular disc?
Circular disc. I'm using circular disc.
Okay. Thank you.
There's just one question from Abhinaya, which is what is the reason to maintain the nitrogen atmosphere during the addition of the additives?
In order to increase the electrical conductivity of strontium titanate base sample, we have to reduce the sample, so that we are using the hydrogen atmosphere. Reducing in the sense, in order to make the sample conductive, we have to make the oxygen vacancy in the sample, so that we are using hydrogen and nitrogen atmosphere.
So to increase the oxygen vacancies in strontium titanate.
Yes.
Yep. Thank you. So we'll leave it at that for this session. So I'll thank all the speakers of this session once again. I know we ran a bit over time, but thank you all for your presentations, and enjoy the rest of the conference. Thank you.
Madam?
Yes.
Yeah. Thank you, Professor Madhu Bhaskaran, for accepting our invitation and chairing this session. On behalf of organizing committee, we are extremely happy to have you here. Thank you.
Thank you. Thank you very much.
Yeah.